Hi everyone, this is my neural communication presentation for my biology class 515, and my name is Precious Dialeg. So before we get to the main idea of our video today, which is the excitatory and inhibitory postsynaptic potential, I wanted to give us a refresher on the parts of a neuron so we can see how an action potential travels down and how these neurons interact with each other. So first we have dendrites, and then we have the nucleus and the cell body. Here we have the axon with the myelinated sheaths. And at the very end, we have our axon terminals. So when an action potential is received from another neuron, which is indicated by these orange arrows here, the signal travels down the axon all the way to the axon terminals. Now, if you want to look at how an action potential works in terms of voltage or membrane potential, we might see a graph like this that shows the change in membrane potential over time. There are three distinct changes that occur over the course of an action potential. We have depolarization, we have repolarization, and hyperpolarization. Now we're going to see what these words mean when compared to the resting potential. We're going to put a value to our resting potential, which is negative 70 millivolts. As we can see, the depolarization portion of the graph increases to negative 60 millivolts, which means that the membrane becomes more negative. Looking at the repolarization portion, we see that it goes back down to the resting potential of negative 70 millivolts. Finally, when we look at hyperpolarization, the membrane potential actually becomes more negative, which ensures that the signal continues downward. So we're going to return to this picture right here, and we're actually going to zoom in into one of the axon terminals at the end of a neuron. So here we have the axon terminal of a neuron. Then we have the synaptic cleft that separates it from the dendrite of the next neuron. When an action potential travels down the axon and reaches the axon terminal, it causes vesicles containing neurotransmitters to be released through exocytosis. These neurotransmitters travel past the synaptic cleft and meet up with the membrane-bound receptors on the dendrite of the next neuron. Now, this is where we get to the main part of our video, which is the two types of synapses that occur. The first type is the excitatory synapse. The second type is the inhibitory synapse. The factor that determines what type of synapse occurs depends on the neurotransmitters that are released. These neurotransmitters bind to the postsynaptic membrane, where they affect ion permeability. So let's explore the excitatory postsynaptic potential first. So just like the other diagram that we drew together, we have the presynaptic neuron here and the postsynaptic neuron here with the synaptic cleft separating them. An action potential will travel down. The neurotransmitters will get released into the synaptic cleft. In the case of the excitatory postsynaptic potential, there are actually specific types of neurotransmitters that are specific to this scenario. So we have acetylcholine, epinephrine, and histamine. So once these are released, again, same thing, these neurotransmitters will interact with the receptors at the postsynaptic neuron, where now they will open up these ion-gated channels, letting in positive ions such as sodium and potassium. So now if we compare this information to the graph that we looked at earlier in terms of membrane potential and time, if this was the value of our threshold, and again this is the threshold that we need to hit in order to start action potential, we have this green line here which represents the excitatory postsynaptic potential. So what this does is it actually brings the membrane potential closer to the threshold. What this means is that the neuron is actually more likely to fire an action potential because it's moving so much closer to that threshold. So now we're going to take a look at the counterpart, which is the inhibitory postsynaptic potential. So same thing as before, we have our presynaptic neuron and our postsynaptic neuron. In between is the synaptic cleft. We have an action potential coming in, which again will signal the neurotransmitters to be released into the synaptic cleft. In this case, however, we have different types of neurotransmitters, such as serotonin and GABA, which are the main inhibitory neurotransmitters. When they attach and bind to the receptors, they will open the ion-gated channels, which will allow an influx of chloride ions in, making the membrane potential more negative. So again, we're going to compare this in graphical form. So here is time and our membrane potential. The threshold for an action potential is signified by the blue dotted line, and we have the green line which represents the inhibitory postsynaptic potential. So as you can see, there's actually a hyperpolarization that occurs here, which means that it takes the membrane potential away from the threshold. So let's go ahead and compare the differences between these two. So the excitatory postsynaptic potential, or EPSP, will more likely cause a neuron to fire an action potential. Whereas the inhibitory postsynaptic potential, also known as IPSP, will less likely cause a neuron to fire an action potential. But what happens if they fire at the same time? It's not just one or the other scenario here. What can happen if that occurs? They actually cancel each other out depending on the magnitude of both the signals. One might overpower the other, but pretty much if they have the same strength of signal, they might just cancel each other out. So our textbook by Sherwood actually gives us a great example of how these two work together, or maybe even against each other. So we've all experienced the need to go to the restroom when it's not a convenient time. Teachers experience this all the time. So this is where we see these postsynaptic potentials in play here. The EPSP, which again is the excitatory postsynaptic potential, causes our bladder to contract, signaling us that it is time to find a restroom to expel our urine. Again, sometimes that's not the easiest thing to do. Then comes in our IPSP, which signals our brain to stop the contractions, otherwise we might have a little accident. And sometimes you can hold it for maybe a few minutes, maybe an hour, maybe even more than an hour, depending on how much liquid your bladder holds or even the type of liquid that you have ingested. So the EPSP and the IPSP working together is actually an example of the postsynaptic neuronal integration. Because our neurons pretty much, they quote-unquote decide what signals to pass on. Right? So they can, put out a signal that says, okay, go ahead and urinate, you're in the restroom now. Or they can say something like, no, don't go yet, you're not anywhere near a toilet. right? So, however, though, we cannot hold our urine indefinitely. If we do not find a convenient time or place to urinate, then the EPSP could overpower the IPSP, which then will cause us to have an accident. I hope you guys found this video helpful, and thank you for watching.